Hello everyone, so today we're going to go over section 2.2, reflections and stretches. So a stretch, unlike a translation or reflection, changes the shape of the graph. However, like translation, it does not change the orientation of the graph. So there are, just like before, two different types of stretches. One is vertical and the other horizontal. So once again, the vertical stretches, just like vertical reflection before it, has to do with the output of the function or the y values. So if it's multiplied by some non-zero constant a, as you can see here, as we can see here, we have y equals a f of x, then the graph will undergo a vertical stretch by a factor of the absolute value of a. Because if a were negative, then it would be a stretch by a factor of absolute value of a and also a reflection as well. Okay, so it also says here if y was replaced by y over a, and that has to do with the fact that we can see y equals a f of x, and then if we divide both sides by a, this is the same as y over a is equal to f of x. So on the other hand, if the x values were, sorry, if x was multiplied by a non-zero constant b, and we have y equals f of b times x, or simply replacing x with b times x, then it is a horizontal stretch by a factor of 1 over the absolute value of b. Okay, so the best way to look at how it works is to actually look at some graphs. But once again, just right here, this statement is about what happens if a or b were negative, and that is the graph will also be reflected in the x or y-axis respectively. Okay, so we have here a function, this one right here, and it's going to undergo some stretches. So in the first example, example 3a, we have y equals 2 times f of x, and then y equals 1/2 times f of x. So to make it more clear, we are going to once again be using the key points on the graph in order to vertically or horizontally stretch it. Okay, so it's going to indicate what colors we're using. We're going to use red for the first part, and then maybe blue for the 1/2. And then after that, for the horizontal stretches, we will use orange and green. So one way to look at vertical or horizontal stretches is to look at the points on the original function. So the original function has 4 key points, and they are -4, -4, going from left to right. Next up is -2, -2. Follow that with 2, -2. And finally, 4, 2. Okay, so the first example, example 3a, part 1, the red part, we have y equals 2 f of x, so the y values will be doubled. Right, so imagine if we were substitute in here -4, then we should get f of -4 is -4, and -4 times 2 will give us y equals -8. So that is to say the first point that we have on the new graph will be -4, -8. And second point, likewise, will be -2, -4. Follow that with 2, -4. And finally, 4, 4. we'll simply plot those points here. So this is going to move the graph. 4, sorry, -4, -8, -2, -4, 2, -4, and finally 4, 4. Okay, and then we connect the dots. And we have a graph that is the same graph as the original, but vertically stretched by a factor of 2. Okay, so likewise, we can also look at the blue graph. Actually, I'm just going to move these, oops, a little bit. It's taking up a lot of space, so that's not what we want. Because we have to fit the second part of the example here as well, so it's going to rewrite this slightly. Again, -2, -4, 2, -4, and 4, 4. And now the next graph, vertically stretched by 1/2. So instead of -4, -4, the new point will be -4, -2. The y values will be halved, followed by -2, -1, followed by 2, -1, and finally 4, 1. And of course, we can go ahead and plot those points. So here they are. 1, 2, 3, and 4. Okay. So as we might expect, the x values don't change, only the y values did. And so it's the blue graph looks like it's compressed closer to the x-axis. So that will be a vertical stretch by 1/2, right? Vertical stretch by a factor that's less than 1. Well, greater than 0, but less than 1. Okay, so another piece that we can examine as well, of course, are the domain and ranges of each one of these. So the domain of the original was -4 to +4. The range was from -4 to +2. And since the graph only underwent vertical stretches, the domain will stay the same for both the red graph and the blue graph. So this will still be -4, 4, and -4, 4 for the domain. The range, on the other hand, will change. Of course, the red graph will have a greater range from -8 to +4. Okay, and the blue graph will have a smaller range going from -2 to +1. Okay. So next up, we have the horizontal changes. So this will be in orange and green. So let's look at the values here. We will have negative, see here, oh, right. So let's go back up for a second. So what is important to note is that the first graph, this was a vertical stretch by 2. The blue graph was a vertical stretch by 1/2. Okay, so if we're not careful, it will look like y equals f of 2x will be a horizontal stretch by 2, but it's not. It's actually the reverse. It's actually a horizontal stretch by 1/2. And y equals f of 1/2 x, that is the horizontal stretch by 2. And a good way to think about this is in the vertical stretches, if we were to place the a value, and that is the 2 or the 1/2, with its variable, which is y, we get y over 2 is equal to f of x, and that's a vertical stretch by 2. And then in the second part, this is 2y equals f of x, and that was a vertical stretch by 1/2. Okay, so it's important to note that's how the coefficients work with regards to horizontal and vertical stretches. Right, back to the examples themselves. So horizontal stretch by 1/2 means the x values are halved. So instead of -4, -4, we'll have -2, -4. Follow that up with -1, -2, and then 1, -2, and finally 2, 2. Okay, let's go ahead and plot those 4 points. So -2, -4, -1, -2, 1, -2, and finally 2, 2. Yep. So the same graph, but made narrower, which makes sense. Okay, so now for the y equals f of 1/2 x, which of course is a horizontal stretch by a factor of 2. So instead of -4, -4, we'll have -8, -4. Follow that up with -4, -2, and then 4, -2, and finally 8, 2. Okay, seems like I wasn't thinking too far ahead, so here's the point 8, 2. It's going to be in the way of our coordinates here, but that's okay. And then we have 4, -2, -4, -2, and -8, -4. All right, so let's go ahead and plot those. Connect the points together. There we have it. All right, so the same graph, but twice as wide. In the domain and range, of course, the y values don't change. It's just the x values that do change. So the new domain for y equals f of 2x would be -2, 2. And the range is the same as that of the original graph, which is -4 to +2. And the domain and range of the green graph, y equals f of 1/2 x, would be -8 to +8. And then the range, that does not change, so that would just be -4 to +2. All right, so a quick example on how to horizontally and vertically stretch graphs. Okay, let's get some other examples as well. Of course, some of them having to do with the equation itself, or points that are on the graph, just like this one right here. So next up we have the point 3, 1 lies on the graph of y equals f of x. What are the coordinates of its image a prime on the graph of y equals 2f of 4x? Okay, so let's see here. This color. All right, so what does this 2 do? Well, that's a vertical stretch by 2. And then we have 4, which is a horizontal stretch by a quarter. So simply put, then we have a prime would be 3 times a quarter because of the horizontal stretch by a quarter. And then 1, which is the y coordinate, times 2, since the graph is vertically stretched by 2. So a prime coordinates would be 3/4 and then 2. Okay. It's probably the most straightforward way to thinking about this. All right. Actually, just gonna change its color here. Not that means anything, but so this would be horizontal stretch by quarter. It's important to be careful about, especially with horizontal stretches. The moment that we see a 4 doesn't mean a horizontal stretch by 4. It means a horizontal stretch by quarter. So that's important to note. Okay, let's see what else is there. Write an equation for the image of y equals f of x after each transformation. Okay, so this is going to be a combination of reflections and vertical and horizontal stretches. Says here reflection in the x-axis and then a vertical stretch about the y-axis by a factor of 2. All right. So a reflection in the x-axis means negative y equals f of x, or simply y equals negative f of x. Okay, and then vertical stretch by a factor of 2, that will give us y equals to, well, this can also be written in two ways. Y over 2 equals f of x, or y equals 2f of x. So these can be combined together, and the result would just be y equals to negative 2 f of x. Okay, and that's it. So, it's an example of combining multiple transformations. For now, we're just going to combine reflections and stretches, but later on we can also combine with these translations as well. Okay, so next up, a horizontal stretch about the y-axis by a factor of 1/2, and a vertical stretch by a factor of 1/4. All right, so simply put then, this be y equals to horizontal stretch. Let's do the vertical stretch first, by a quarter, so 1/4 f of x. But this, of course, will be f of 2x because of the horizontal stretch by 1/2. Okay, so again, this is where the f of 2x came from, the horizontal stretch, and then the vertical stretch is where the 1/4 comes from. And then we combine them to get the result. Not doing a good job using the colors, but hopefully it still makes sense what the final answers are. Okay, next up, a horizontal stretch by a factor of 6. So that would just be y equals to f of 1/6x, quite simply. Vertical stretch by 1/5. So this would simply be y equals to 1/5 f of x. Alrighty. So let's next up is another way of phrasing basically the same question. Example 5, how does the graph of 3y f of x compare to y equals f of x? So, best way to look at this question is probably just to rewrite it. Notice that 3y f of x, sorry, 3y equals to f of x is the same as y equals to 1/3 f of x. So of course, that just means we have a vertical stretch by a third. Okay, pretty simple. And then another way of looking at these transformation is by replacing x and y. Sorry, x or y or both. So in the first example here, we are replacing x with 4x. So instead of y equals f of x, we have y equals f of 4x. And that, of course, is a horizontal stretch by a quarter. Okay, next up, replacing y with 1/3 y. So this would be 1/3 y equals f of x. So y equals 3 f of x. And that will be a vertical stretch by 3. Okay, finally, last part, 2 replacements. So we have 6y is equal to f of 1/3 x. Okay, so y is equal to 1 over 6 x, sorry, 1 over 6 and then f of 1/3 x. That's better. So this would be both a vertical stretch by 1 over 6 and also a horizontal stretch by 3. Not 1/3, but 3. Alrighty. Okay, just a couple more graphs to combine multiple transformations. But before then, we have here an actual graph. So you recall that this is the semicircle graph. And we're going to transform it with vertical stretches and then horizontal stretches. All right. So the first one is pretty straightforward. Right. Vertical stretch by a factor of 2. So that means we have y equals 2 multiplied by the entirety of f of x, which was the square root of 25 minus x squared. So, and that's all we need to do. Okay, next up, same thing, but instead of a 2, we have a quarter. So something like this. And then horizontal stretch by a factor of 5. So we need to replace x with x over 5 of 1/5 x. So that's a little bit different. So let's do that. We have y equals 2, and then 25 minus, I'm just going to write as 1 over 5x, and then squared. Now, of course, this could be expanded, but it's not entirely necessary to do that. There's not much to be gained by expanding here. Again, x over 5 is also acceptable. X over 5, and then in parentheses squared is also acceptable. And finally, horizontal stretch by 1/3. So this would be y equals to 25 minus 3x all squared. Now this one will expand because it should be mentioned what happens when we do. The whole of 3x will be squared, so this will actually be 25 minus 9x squared all underneath the square root sign. So that's important to note. Right, so imagine in the previous example, the one on the left, what would happen is we will square the 1 over 5x, and so we'll get x squared over 25. But it doesn't simplify. It does, but it's it's okay to leave it as is. Okay, so I'm going to sketch some graphs with stretch and a reflection. We have here y equals f of x, which looks like the absolute value function. Sketch graph of y equals negative 1/3 f of x. Okay. So two transformations are happening here. There is the negative sign, which reflects the graph over the x-axis, yes. And then there's the 1/3, so that will be vertical stretch by 1/3. All right. So good way of doing this is to, once again, as usual, look at some key points on the graph. So in this case, we'll look at 0, 0, and then negative 3, 3, and then 3, 3. And the reason why the threes were chosen is looking ahead to the vertical stretch by 1/3, probably advantageous to work with those. And then it says to state the domain and range of each function. Well, we're going to make the assumption that the original function here is the absolute value function, even though we don't know if the graph continues on. So if it were a absolute value function though, then the domain is x is an element of the real numbers, and the range is going to be y is greater than or equal to 0. Okay. And what we're going to do is to list those 3 points. So that's negative 3, 3, 0, 0, and then 3, 3. So look at what happens after the transformation. There's a reflection over the x-axis, which means the y values become negative versions of themselves. So 3s will become negative 3s, but the 0 will stay the same. And then afterwards, there's also a vertical stretch by 1/3. So taking both of those transformations under consideration, we will have the new points negative 3, negative 1. 0, 0 will stay the same, so that will be an invariant point. And then afterwards, the next point will be 3, and then negative 1. Right? So think about it as the y values being multiplied by negative 1 and then multiplied by 1/3. It's not a bad way to think about it. I'm just going to write here y values, and then they're multiplied by essentially negative 1/3. Alright, so the new points then will be here, and also the 0, 0, of course, as before. Connect the dots here to form the graph. Something like this. Okay, so kind of what we expected. The graph will be upside down because of the reflection, and also compressed vertically because it is vertically stretched by a factor of 1/3. So let's write down the domain range as well. The domain, note the domain doesn't change because neither of the transformation were horizontal. And then the range, there was a reflection, so the range is going to be y is less than or equal to 0 now. Okay, so let's look at one more. A more complex looking graph. Let's begin by looking at the original points. There are 4 of them, 1, 2, 3, 4, moving from left to right. They were negative 4, negative 6, followed by negative 3, and then positive 6, followed by 3, 4, and finally 6, negative 2. All right. And now, what are the transformations? Well, or there are two transformations. The first one, this is a reflection over the y-axis. And then there's also a 2, oops, which is a horizontal stretch by 1/2. All right, which means the x values would be made negative and then halved. So the new points would be 2, -6, and then 1/2, sorry, 1.5, +6, and then -1.5, 4, and finally -3, -2. Okay, so let's see here, -3, -2, that's the first point. -1/2, 4, sorry, 1.5, 4. +1.5, 6, or 1.5. And then 6, and then finally 2, -6. 2, and then -6 down here. Alrighty, and then we can connect the new points together using straight lines to make the image graph. And that's it. So things to note about this graph. Once again, we're going to state the domain and range. Let's make a table to do this. So domain, and then range. The domain and range of the original function goes from -4 to +6, and then the range goes from -6 to +6? Yeah, that's right. Alright, and then the domain range of the transformed graph goes from -3 to +2. And of course, the range is the same because neither of the transformation were anything to do with y coordinates. So finally, it is entirely possible to have functions that are both vertically and horizontally stretched at the same time. And in the next section, we'll look at that combined with translations and reflections as well. But that's it for today, so thank you for listening.